Okay, in this section we are going to be studying exponential functions. And so what makes something an exponential function is when the variable is in the exponent spot. So down below here we can see that f of x equals a times b to the x power. The power is a variable, so that's kind of our setup for an exponential function. A is a non-zero number, and your initial value is when x equals zero, or basically you're saying that's your y-intercept. When x equals 0, that's a y-intercept. So that's kind of what we're looking at here. B is positive and the base is not equal to 1, and B stands for your base. So that's kind of your generic setup for your exponential function. So down below we have some examples, and where it says identify if the following are exponential functions. If yes, name the base and the initial value. So on part A, yes, it's an exponential function. The variable right here is in the exponent spot. So that's going to be a yes. This is the base attached to it. So the base is 3. And the initial value is when x equals 0. So over here, let me rewrite this. If you put a 0 and out in front is your a value, right here is supposed to be the a, and this is the b. So right now the a is 1. We just don't write it because we don't write 1 times 3 to the x. If you put a 0 in for x, because that's your initial value, or your y-intercept, 3 to the 0 power is 1, so y equals 1. So the initial value is 1. Okay, letter B, g of x equals 6x to the negative 4 power. Nope, this is not an exponential function. That power right there is negative 4. It's not a variable. Okay, letter C, we have h of x equals a negative 2. And then our base is 1.5 raised to the x power. So yes, that is a variable. The power is a variable. So yes, this is an exponential function. This negative 2 is representing the a. The 1.5 is representing the b. So my base is 1.5. And what's my initial value? Well, if you put 0 right here for x, then that means 1.5 to the 0 power is 1. So negative 2 times 1 is still negative 2. So a turns out to be your initial value, negative 2. Okay, looks like to me we have an exponent that is a variable. So yes, this is an exponential. The base is 2, and the initial value is 7. And then letter E, q of x equals 5 times 6 raised to the pi power. That's not a variable, so that one is a no, it's not exponential. So remember, exponential functions, the power is where the variable is located. Okay, so this says use a calculator to evaluate each function at the indicated value. So this is just kind of a exercise in running your calculator and finding the right buttons. So you want to get your calculators out. So this first one, we're going to say y equals 2 to the x, and so in our calculator we're just going to take 2 and raise it to the negative 3.1 power, and when we do that we end up with we'll go to 2 decimal places, so approximately, oh, let me fix that, 0.12. Okay, letter B, we have f of x equals negative, or excuse me, f of x equals 2 raised to the negative x power. So we got y equals 2 to the negative x power. So when we substitute that in, we're going to say 2 raised to the negative pi power. So y is approximately, so we're going to 2 raised to the negative, you should have a pi button on your calculator, pi power. And that is about 0.11. And the last one we have f of x equals a negative 0.0 or 0.6 raised to the x power. So when I go ahead and type that in my calculator, we're going to have 0.6 raised to the 3 halves power. So y is going to be approximately 0.46. Okay, so that was just a calculator exercise, just making sure you substitute in correctly and keeping your power in the power spot. Okay, so what does the exponential graph look like? So first of all, you have growth and decay, and you may remember those from ninth grade. You do a little bit of them last year in Math 3, but majority of the studying of the growth and decay, I think, was done in the ninth grade. So this says f of x equals a times b to the x minus h plus k. Our H and K's, these do the same eight things that H and K has always done. That's our left and right and up and down translations. B is your base. A is still your initial value. It's going to be a growth right here. This is going to tell you if it's a growth or not right here. If B is greater than 1. So if this base right here is greater than 1, it's going to be a growth. And that is also if our A is positive. So kind of highlighting this right here as A being positive. Whoops, right here. Okay, so if you were going to graph the generic growth function, what happens is your initial value is 1. So you cross your y-intercept at 1, and you have a horizontal asymptote. The x-axis is the horizontal asymptote. And so your growth function kind of looks like this. As you move left to right, it's increasing. And on the left, your boundary is the x-axis. That's your horizontal asymptote, y equals 0. That's your limit. It approaches y equals 0. As you move left, as you go closer and closer to negative infinity, it gets closer and closer to 0. And as you move right and you go towards positive infinity in the x direction, your y values start to increase exponentially. They increase faster, depending upon what your growth rate is. Okay, so this one right here, this one's talking about exponential decay. Now, the one on the left is the traditional way of writing the exponential decay, where A is still your initial value, B is your base, your H and your K are doing your left and right and up and down translations. On this scenario, though, the base right here is between 0 and 1. So basically your base is some kind of, like 0.5 or 0.75 or 0.6, whatever. It's between 0 and 1. And that's also true down here highlighting when A is positive. When A is negative, we have something totally different happening, because remember, if it's A is negative, it's going to reflect your graph. So this is not reflecting up and down at all. Or another way that you could write that is if you ended up with, over here on the right, if you end up with your x value being negative in the exponent spot, so like a negative x plus 3 or a negative x minus 5, it doesn't matter. If that x is negative, then if your b happens to be greater than 1 in that scenario, it will also be a decay. And why is that true? Well, let's just go back to something like this. Let's just go back to I'll say 1/2. And if I raise that to the negative 1 power, that's the same thing as 2. And vice versa, if you have 2 and you raise it to the 1/2, a negative 1 power, that gives you 1/2. So right here, if we want our b to be less than 0, then, and we have a negative x, then you're going to want that base to already be greater than 1 right here. See how 2 is greater than 1? If I do the reciprocal of that, I get 1/2, which puts it between our boundary that we had over here on the left, where b is less than 1 and greater than 0. So in that scenario, guys, when you're talking about the decay function, so you got growth and decay, same thing still happens. Your initial value is still here at 0, 1. You still have a, whoops, I missed. You still have a horizontal asymptote, and it just, as you move to the right, it's decaying. The y values are getting smaller. So on the left, as you go further left in the x direction to negative infinity, your y values increase. And then as you move to the right, they get closer and closer to y equals 0, that limit, that horizontal asymptote. So that's our exponential decay. So we've got growth and decay. Sometimes I might say increase and decrease instead of growth and decay. We're talking about the same thing. So here we've got 4 different graphs, and we're supposed to graph them all on the same coordinate plane. Just a quick look down on all of these. I noticed that A is 1 on all of these. So my initial value is going to be 1. I don't have any up and down, anything plus on the end or anything with the x left and right. So I'm not translating it anywhere. So basically, all of our graphs are going to come through this point right here, 0, 1. Well, what's going to change? If you were going to graph y equals 2 to the x, and you were going to graph that, so let's just do a quick table here. I already know that at 0 it's going to be 1, because anything to 0 power is 1. Let's see what happens on the right-hand side. If I pick 1, 2 to the 1 power is 2. If I pick 2, 2 squared is 4. So on the right-hand side, you can see as you go over 1, you're starting to increase. You're doubling because it's got a base of 2. So here we go. We're going, and then if I put in 3, we would end up with 8. So 3 is now at 8 right there. So we can see it's starting to go this way, increasing. And then what would be happening if I did negative 1? Well, negative 1 would give me 1/2. So I can see that I'm starting to approach my limit here on this side. Okay, so there's that first graph. Okay, what would happen if I have a negative x? Well, if we're going to go by what just happened, if we were to talk about what happened in last chapter about the negative x out in front, remember that was your left and right reflection. So if 2 to the x is a growth, then 2 to the negative x is probably going to be a decay. If that's the only thing that changed, well, let's just make a quick table and see what happens. Put a 0 in for x, and yep, we're still crossing at 1. Let's put a 1 in. 2 to the negative 1 power is 1/2. Yep, there we go. I put a 1 in and I got a 1/2. Let's see what happens on the other side. Let's put negative 1 in. So 2 to the negative 1, right? That doubles. So that's going to be 2 to the 1. So that's 2. So right here. So yep, this graph is going to go like this. Okay, that's going to be a decay. All right, what happens then when I have a base of 1/2? Well, a base of 1/2 is supposed to be a decay. Well, let's just see. When I put a 0 in, I get a 1 out. So yep, that one's starting in the same spot. What happens when I put a 1 in? I get 1/2, right? Because 1/2 raised to the 1 power is 1/2. So look, I'll get that decay right there. I'll just kind of draw that dotted over the red one so we can see it's the same graph. Let's just check negative 1 and see what happens. If you put in 1/2 and you raise it to the negative 1 power, that's going to give you 2. So yep, that's going to be a decay, which we thought it should be. So then I'm thinking down below here then, if the one above it's a decay, then this one should probably be a growth. If I'm going to do 1/2 raised to the negative x power, let's just pick a number, put a 0 in, we get a 1 out like we said from the very beginning. And then let's put 1 in. So now we have 1/2 raised to the negative 1 power. Well, that's the same thing as 2. So when I put a 2 in, I mean, a 1 in, I get a 2 out. Here we go. So there we go. That's going to follow the growth. That's actually going to turn out to be a growth and not a decay. All right. So depending upon that exponent's sign, meaning the x is positive or negative, that really affects what the b is. So if x is positive, so when x is positive and the base is greater than 1, it's a growth. And when x is positive, oops, that looks like 2 x's in a row. When x is positive and b is less than 1 and greater than 0, it's a decay. Decay. And then when x is negative, that just flips everything now. When x is negative and b is greater than 1, it's now a decay. And if x is negative and b is less than 1 and greater than 0, it's now a growth. So you got to pay attention to that sign, meaning positive and negative, on the exponent for your exponential function to decide whether it's a growth or a decay. All right, so what happens then with the negative sign out in front? So basically we could take the pictures that we had on the other slide. So 2 to the x went like this. Here's 2 to the x to the 8, right? So, and then we went to a half. So this was y equals 2 to the x. That's y equals 2 to the x. So if you want y equals a negative 2 to the x, then since this a out in front is negative, that's going to reflect it down. So your graph is going to be not going up. This one we wouldn't call a growth or a decay. It's just kind of got a reflection going with it. So what would you end up with points? Well, if you want to figure that out, you could just do a table of values, put the 0 in for x, and you get 2 to the 0 power, which is 1, times negative 1, so it's now negative 1. So here we go, negative 1 right here. And then what happens if I put a 1 in? Well, 2 to the 1 is 2, times negative 1 is negative 2. So you can see how that reflection is working. It's going to reflect down like that. Okay, so if we had negative 2 to the negative x power, so let's just flip back to that other slide. You probably have it there in your notes. That one was our red one, so that was our decay. So if we're going to reflect that, then that is going to come down. It originally went like this, right here like this. So we're going to reflect it down, and so it's going to go the other way. It's going to go this way and down like that. Guess I could do that in a non-highlight color. Let's get rid of that. And we'll just do this in a solid green. Whoops. So it looks something like that. Okay. So you get the idea. So then the next one, the negative out in front, if you look at your previous picture, the 1/2, that was our blue, that was a decay. So that's going to turn out to be the same graph as the green one that we just did. And then letter D, the negative, that one is our black, dotted black graph. So if we're going to reflect that down, that's going to turn out to be the same as that blue graph. Okay. So you just got to keep track of, are you reflecting up and down, or are you reflecting left and right? Basically, when you talk about growth and decay, though, we only call those growth and decay if you're talking about the left and right graph, not the reflecting up and down. So when we talk about growth and decay, we're just basically talking about this shape and this shape. Even though you can reflect those shapes in up and down, growth and decay are only going to refer to those two. Okay, this one, now we're going to just describe the transformation. So it says describe the transformations of the graph of f of x equals 4, our base is 4, to the x power that yields the graph of each of the following functions. Okay, yields, looks like that is spelled wrong. Let's fix that typo here. I'll fix that in a minute. Okay, so here we go. G of x equals 4 to the x minus 2. So same base. This is my h right here. So right here I'm going x minus 2. So that's going to go right 2. It's just going to take that exponential function and it's going to move it right 2. Here we have a plus 3 on the back end. So that's like your k. So that's going to go up 3. And k of x, looks like I got two things going on. So I see this negative sign right here with the x, so I know that's going to reflect in the y-axis. So that's going to make it reflect the other direction. And this minus 3 is going to go down 3. So this one says, now down below, state how the y-intercept and the horizontal asymptotes are affected. So on letter A, if you want to figure out what the y-intercept is, remember that's putting in x equals 0. So let's go back up here to part A now and see what happens. Y equals 4 to the 0 minus 2. So that's going to be 4 to the negative 2 power, which is 1/16. So it looks like my y-intercept is now 0 1/16 instead of 0, 1. Okay. Part B, and then the asymptotes. So the asymptotes don't change on this one, because if you're only moving right, that won't change any asymptotes. If you're moving left and right, that won't change any asymptotes. So the asymptote doesn't change. So on part B, h of x equals 4 to the x plus 3. Well, if we want to figure out how that changed the y-intercept, it's going to be 4 to the 0 power plus 3. Well, 4 to the 0 is 1. 1 plus 3 is 4, right? So the y-intercept is now 0, 4. So that actually moved the y-intercept up one spot. Oh, excuse me, 3 spots. Sorry. We went from 0, 1 to 0, 4. So it moved it up 3. And this one will also take the asymptote. Since you're moving up and down, your asymptote, your horizontal asymptote, instead of being at y equals 0, it's now going to be at y equals 3. It's going to move it up 3 also. Okay, and then part C, if we go ahead and do the work on that one, we get y equals 4 to the negative, and then you put 0 power, but 0 is not positive or negative, so that's 1 minus 3. So that's going to give you negative 2. So your y-intercept is going to be 0, negative 2. And what's going to happen to your horizontal asymptote? Well, right now, the horizontal asymptote is at y equals 0. As soon as you shift it down 3, your new horizontal asymptote is going to be y equals negative 3. So when you go to graph, it's kind of important to know what's going to happen to your y-intercept and your horizontal asymptotes. Okay, so when we're graphing, we can always do a table of values for this. We can pick a table of values. We could type it in our graphing calculator and see what it looks like in our graphing calculator. But we kind of want to start out using what we know about the generic shape of the graph and how it's affected by transformations. So what I mean by that is this one right here's base is 3. Its initial value would be at 0, 1. But this x minus or x plus 1 is actually moving everything left. We're going left 1. Okay, that's not going to change your horizontal asymptote. Moving a horizontal asymptote left 1 just still keeps it on the x-axis. So there's my asymptote. Now, I do know that on all exponential graphs, the initial graph without any transformation crosses the y-intercept right there at 1. Its initial value is 1. Well, since I know that's a graph and I'm moving it left 1, it looks like to me I'm going to take this one, I'm going to move it left 1, and now my y-intercept is going to change, but it doesn't change the fact that I'm still going to graph a growth function. If I want to see what my y-intercept is, I could put 0 in for x, and I can see if I put 0 in for x, if I want to see where it's at, I'm going to get 3 to the 1 power, which is 3. So my y-intercept is going to be at 3 now. So I've got 1 point here, and I now have my new y-intercept at 3. I know it's supposed to be a growth, so I could just sketch this. That's enough to figure out what's going on. I've got my asymptote. Make sure you always show your asymptote. I always want you to show this key point right here, this one that gets shifted around. And then if you can find the y-intercept, find that one also. So those are things that I'm going to be looking for on your graph. All right, so let's look at letter B. So if I were just going to describe what's happening, it looks like to me I'm going right, 2, and up 1. Okay, normally my asymptote is the y-axis, or excuse me, the x-axis. It's y equals 0. If I'm going to take that and move it up 1, this is now my asymptote right here. It moves up 1. This key point that is normally right here at 0, 1, that key point is going to move right 2 and up 1. There it is right there. Okay. And if I want to figure out what the y-intercept is, I can put the 0 in. So that's going to be 2 to the negative 2 power plus 1. And so that's going to turn out to be 1/4 plus 1. So that's 1 and 1/4. So 5/4. So that's just barely above my horizontal asymptote. So I'll put that right there. And I know that it's supposed to be a growth, so I'm just going to make that sketch just like that. Okay. So make sure you draw your asymptotes. Make sure you draw the initial point, how it translates moving. And then if you can find your y-intercept, find that one also. And then the rest of them, you can do as many points as you want, but you could just sketch the right shape after that, and I'll be fine. That works for me. You could type it in your graphing calculator to double check if you want to make sure you're doing it right. Okay, so this one right here is a special exponential function, f of x equals e to the x. It's special because e is a special number. This is Euler's number. You should have the e button on your calculator. I think some of the calculators have it in more than one place. How he figured out, you know, how um, pi times diameter, how the number pi is the circumference divided by the diameter. That's how they get pi. That's how they approximate those digits. You can take the circumference of any circle, divide it by its diameter, and you're going to get approximately 3.14, blah, 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 blah. Well, they did the same thing for the letter E. Euler came up with this formula, and it said the limit as x goes to infinity. So that means as you start picking x's and as you go to positive infinity, so you're not going to pick any negative x's, you're going to pick positive. As you start to put them into this formula over here on the right, you're going to get closer and closer to this number, 2.7182. You can type it in your calculator to see what it is. And you could do that if you wanted. Like you could take x's 10. So what are you saying? You're saying 1 plus 1/10 raised to the 10th power. You could type that in your calculator and see what you get. You could type in 50 and see what you get. The higher the number, you're going to start to get closer and closer to 2.7182. That's going to approach that number. So that's how they came up with the number E. That's where its number came from. So, natural, wow, I got a lot of typos here. Nice spelling there. We're going to have to fix the spelling on that one also. Okay, so what does the graph look like? Well, the base is 2.718, so that means B is greater than 1, so that must be a growth. So normally, initial values right there, and it would just be growing like that. Okay, so it's a growth because B is greater than 1. All right, so now we're going to switch gears a little bit, and we're just going to do a little bit of solving of exponential functions that are one-to-one. So basically, they want you to figure out what x is. And this is going to go back to that worksheet that we did uh, last time with our M&Ms. We want those two to be the same base. So 2 is done. 2 is the base. So we need to rewrite 64 as a base 2. So this is going to be 2x minus 2 equals 2 to what power gives you 64? Well, I think 2 to the 5th is 32, so 2 to the 6th is probably 64. Yep. So once you get the bases to be the same, now all you have to do is set the exponents equal to each other. We can kind of just disregard those bases because it doesn't matter. They're the same, and now we just check the exponent spots. So x minus 2 equals 6. Add 2 to both sides, so x equals 8. Okay, over here, this is 5 to the x minus 2. Right now, I could write that as 5 squared, but that's not the same thing. 5 is in the numerator spot. My 5 is in the denominator spot. So if I move that up and I write it like this, now I can put those two equal to each other. I can say x minus 2 equals negative 2. So x equals 0. That's the solution to that one. Okay, over here, lucky for us, we don't have to type in the base e because they're the same. So all we got to do is put those two equal to each other. 2x minus 1 equals 4. 2x equals 5. Divide by 2, so x is 5 over 2. And same thing over here. Bases are the same, so all we care about is putting the powers equal to each other. 2x plus 6 equals 5x. Combine my like terms, so 6 equals 3x, so x equals 2. Okay, so there's just an application there of rewriting a number so that you have the same base on both the left and the right-hand side so you can compare the exponents. And now we're just going to do a couple of problems that deal with their application problems with exponential functions. So exponential functions usually go into finance. So application there would be finance. So we have two formulas here. A equals P to the 1 plus R over N times T, and then the other one is what we call the PERT formula for short. A equals P E to the RT power. So this is how you find formulas for compound interest. So how much money do you have after a certain amount of time? So P for both of these formulas is the principal. That's what you start out with. Okay, so that's how much money you start investing with or whatever you're putting in your savings account. Okay, the R is the rate. And you're going to want that to be a decimal. So if I say 6%, you're going to want to change that to a decimal, like 0.06. And then N is the number of compoundings per year. So like if I said monthly, that means 12 times a year. So N would be 12. If I said quarterly, that's 4 times a year. So N would be 4. And then T stands for time. So whatever your investment is in years. I think they usually do time in years. Okay. So there's our formula. So let's go ahead and do an application here. So it says you invest $12,000. So that's our principal. at an annual rate of 3%, so we're going to use 0.03. Find the balance after 5 years when the interest is compounded quarterly, monthly, and continuously. So our time is 5. So first of all, for part A, to do quarterly, that means N is 4. Quarterly is 4 times a year. So if I'm going to do my formula, I'm going to say A equals, my principal is 12,000, and then 1 plus my interest rate, 0.03 over 4, because I'm doing this quarterly, and then 4 times 5. Okay, so let's just go ahead and figure out what that is. So on my calculator, what I'm going to do is I'm going to put in parentheses, I'm going to go 1 plus the 0.03 divided by 4. I'm going to get that as 1.0075. Then I'm going to raise that to the 20th power, and then I'm going to multiply that by 12,000. And then we'll have our answer. Okay, so 12,000 times 1.0075 raised to the 20th power, and we end up with $13,934.20. We won't round up. I'm pretty sure there's nobody, banks don't round up. They just cut them off. They just cut the decimals off. They're not going to give you money. So they're just going to cut that off. So we're just going to say we're not going to round up that second spot. You're just going to cut it off 2 decimal places, no rounding. So $13,934. So after 5 years, you've earned what? Almost 19, a little over $1,900. You start out with 12,000. Okay, so what happens if we do the same thing, but now it's compounded monthly? So that means N is going to be 12. So same thing, we're going to say A equals 12,000 times 1 plus, it's a big one, that doesn't go with the fraction over here, 0.03 over 12 times 12 times 5. Okay, well, let's figure out what our numbers are here. 1 plus 0.03 divided by 12. 1.0025, and that's going to be raised to the 60th power. Okay, let's figure out what we have now. 12,000 times 1.0025 raised to the 60 power, and we end up with, wow, just about, pretty close, 13,939.40. So we got a little over $5 more if we compound it monthly. Okay, how much more if we compound it continuously? So new formula on this one. This is our PERT formula. So you got to find your E button in your calculator. So you're going to say 12,000 times E to the, and our rate was 0.03 and our time was 5 years. I guess I don't need this parenthesis here. Let me rewrite that. E to the 0.03 times 5. Okay, so here we go. Let's figure out what that number is. 12,000 times E raised to the 0.03 times 5 power. I just typed it all in at once. And we end up with $13,942.01. So even a little bit more if it's compounded continuously. Okay, this one says find the amount. So when you're looking at these problems, guys, you're going to have to decide how you're compounding. Is it continuous or is it, you know, for a certain amount during the year? That's going to tell you what formula to use. So this says find the amount A accumulated after investing a principal P for T years at an interest rate R, and it's compounded continuously. So when I put it in my formula, since it's continuous, I'm going to use the PERT formula. It's 3,350 times E raised to the R. Now remember, we can't put in 6.2. We got to change that to a decimal, 0.62. And time is 8. All right, so let's type that in. And we end up with 5,300, or no, $5,536.48. Okay, here's another application for exponentials. Down below, I've kind of got some formulas here that you could, it's all the same formula, they just change it a little bit. So this is still our exponential of y equals a times b to the up here, this power right here. So look, your initial amount is still your A. This growth factor is still the B. What changes right here is when you're doing doubling, tripling, that kind of stuff, you just take X and divide it by the time. So that this spot right here is represented by X divided by the time. And your base, if you're tripling, your base is 3. If you're doubling, your base is 2. If you're quadrupling, your base is 4. So half-life takes the same formula. Since you're doing a half-life, your base would be a half. So same thing, they just put P sub 0, meaning that's your initial population. Here's your base as a half. It's all still following the exponential formula. It's all still the same thing. And then T divided by H, time divided by your half-life. So it's still whatever you're working with divided by the half-life or whatever time they give you. So here we go. We'll try one. It says, suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be $350,000, or three, not dollars, sorry, 350,000 bacteria. So here we go. Here is our, we're doubling, right? So we're going to say we want to know when it's going to reach, whoops, 350,000. That's what we're after. And it's doubling every hour. So if we're doubling every hour, then our base is 2. Our initial value was 100. So we started with 100 bacteria in the petri dish. Our base is going to be 2 because we're doubling every hour. And they want to know the time. So that's what we're trying to figure out. Predict the number, predict when the number of bacteria will be 350,000 if it's doubling every hour. So we're going to divide that by 1, the time spot up there. X divided by 1 because it's every hour. So if we're going to go ahead and figure this out, we're going to have to take 350,000 divided by 100. So that's going to give us 3,500 equals 2 to the x power. Okay, so now here, this is where it's a little different because we haven't figured out how to do a logarithm yet to figure out what that x is. So we can do this 2 ways. You can type it in your graphing calculator. So in y1, you can type in 3,500, and in y2, you can type in 2 to the x, and you can see where they cross, and that'll be the x you're looking for. So you're looking for the intersect. Or you could just do a little bit of guessing and checking if you wanted. So you could say, okay, well, 2 raised to, I don't know, I'm going to say 20 power. Oh, way, way too big. That I got a little crazy there. That was like, oh, billions. Okay, so let's tone that down. 2 raised to the, I'll go to 15. Okay, that's a little bit better. That was 32,000, but we only need 3,500. So how about 2 to the 10? Okay, 2 to the 10 is 1,024. So it's got to be somewhere between 10 and 15. So 2 to the, I'm just doing a little guessing and checking. You guys could type that in your calculator if you wanted. Okay, I did 2 to the 12, and I got 4,000. So 2 to the 11. Okay, so it's got to be more than, let's go 2 to the 11.5 power. Getting closer. 2 to the, let's see, say 2 to the 11.7 power is 3,326. So I'm getting closer. So let's say 2 to the 11.75 power. Ooh, so close. 3,444. So how about 2 to the 11.76 power? Oh, not quite. 2 to the 11.78 power. Ooh, that's pretty close. That was 3,516. So I'm going to do 3 to the 11.77 and see what that one is. 2, not 3. 2 to the 11.77. Oh, that one is pretty close. 3,492. So I could go one more decimal place and go 2. We could keep doing this forever, huh? You could type that in your graphing calculator and see. I'm going to go 7 3 power. 773. Oh, so close. I'm going to go with this. X is approximately 11.773 because that turned out to be about 3499.6 in my calculator. Okay, so a little guess and check there. When we learn how to do logarithms, we could solve it exact, or you're going to have to do your graphing calculator to figure that out. Okay, so here's another one. Let Q represent a mass in grams of radioactive plutonium whose half-life is 24,100 years. The quantity of the plutonium present after T years is given by the following formula. So this right here is your initial value, right? It's a half-life, so your base is a half. The half-life itself goes right here, and the time we're looking for, you're dividing by the half-life. So determine the initial quantity when T equals 0. Well, we already said that just by looking at the formula. It's 16 grams. And then determine the quantity present after 75,000 years. So we'll just take that formula. Q equals 16, and then 1/2 raised to the 75,000 years, divided by its half-life. And we'll see how much is left. So 16 times 0.5 raised to the, and I'm just going to put it all in as a fraction, 75,000 divided by 24100, and we end up with 1.85 grams. So after 75,000 years, you end up with 1.85 grams. So half-life, guys, remember how, let's see if that kind of makes sense to us. Let's see. So what half-life says is that in 24,000 years, you'll have half the amount. So if we started with 16, 24,000 years later, about, we're saying, okay, I should have 8 grams, okay? Starting with 8, another 24,000 years later, I should have 4. And then I started with 4, and another 24,000, this is just an estimate, I should have 2 grams. Well, we were checking after 75,000 years, right? So that's not quite 75,000, and I'm down to 2, and our answer is 1.85. I feel like that's a pretty reasonable answer. I think our math is good. I think that looks right. Okay, there you go. We're done.